Okay, so we're more than halfway through chapter 4 now, and we've taken a look at various aspects of nuclear chemistry, and we've tried throughout to have some medical applications and mention those isotopes that are used in medicine versus those that occur in nature, and even compare and contrast the typical half-lives of the naturally occurring radioactive isotopes compared with the medical isotopes. Yeah, of course, the radioactive isotopes occurring in nature tend to be very long-lived, while those in medicine tend to be very short-lived. So we've already made that distinction. Now we'll take a little more opportunity to look more at medical applications. If you think back to the very beginning of chapter 4, we talked about various exposures and how some of the higher exposures to radiation come from medical applications. Background radiation isn't a very big concern because it's pretty small exposures and there's not really much we can do about it anyway, whereas those medical exposures tend to be fairly significant, still, again, worth the risk. Otherwise, we wouldn't do that, but let's take a look at some of those medical applications and why we would willingly expose ourselves to relatively higher doses than normal background radiation. Alright, so as we've already mentioned, it tends to be the radioisotopes with short half-lives that are used in nuclear medicine, and this is because they have the same chemistry in the body as the non-radioactive atoms. So if we look at this thyroid scan, we've already talked about iodine-131, which behaves very similarly to normal iodine, and therefore it's able to be used to diagnose thyroid dysfunction. Also, they give off radiation that exposes a photographic plate, a scan, to give an image of an organ or a particular region, like we see here with the thyroid scan. So they're very nice because they just differ in terms of having a stable nucleus for the non-radioactive atoms and then an unstable nucleus in the case of the radioactive isotopes. So otherwise they behave chemically the same, and the radiation that they emit does allow for an easy imaging of the region of activity. Here we see table 4.8 from the text that lists some medical applications of common radioisotopes. Again, I'm not going to read you every application and every isotope that's used, but what you can see in terms of the trends, they tend to be pretty short half-lives on the order of an hour or a set of hours to days. I think 65 days there for the strontium-85 is the highest in this list. And again, that's because we don't want this radioactivity to linger and to cause long-term problems like mutations, cancers, things like that. We want it to be pretty short-lived. It looks like iridium there, iridium-192 is 74 days, so I guess I was wrong about the longest list on this list. And we see sometimes the whole point is to cause damage. A lot of these are treatments for various types of cancers, and you tend to see that with the gamma radiation. Gamma, high energy, good penetrating ability, very damaging to cells and deadly to those cancer cells, hopefully at a greater rate than the non-cancer cells. Other times it's just for imaging or detection of various illnesses. So depending on the application, either it's a sort of radiation that's to image and diagnose, or oftentimes, as we see on this list, to treat various diseases, especially cancers, by killing those faster dividing cancer cells at a greater rate than the normal cells. So if we look at that one application, that is to have scans with radioisotopes, typically the person would report to the diagnostic imaging area, or sometimes called the nuclear medicine part of the hospital, and they're dosed with the radioisotope. The radiologist has determined the level and location of the radioactivity emitted by that isotope that's already been administered. A scanner is used to produce an image of the organ or target region, whatever it might be. Gamma rays, typically, although we did see beta and positron radioisotope activity as well in that list in the previous slide, but typically it's the gamma rays that can be used to expose a photographic plate because of their good penetrating power, and then areas of decreased or increased radiation can indicate the presence of a medical problem, and that's what we tend to use the scans for, is to image that region that would otherwise be tough to image. Normal x-rays, that would be good for bone, really dense areas of calcified material like teeth and bone show up well, but soft tissue areas, it's much better to use these radioisotopes to get a good image of that region and see if there is an abnormality or disease state present. And so here we see an image of one of those scanners, and it looks like we're focused on this young lady's thyroid, so it's probably that radioactive iodine 131 that's been dosed, and now the detector is imaging that thyroid based on the amount of radioactive decay emitted by the radio-labeled isotope that was administered previously. One specific type of scan, positron emission tomography, a PET scan as it's commonly called, utilizes positron emitters with short half-lives, and here we have a list of 4 common ones: carbon-11, oxygen-15, nitrogen-13, and fluorine-18. One example would be the positron emitter fluorine-18 to study brain function, metabolism, and blood flow. And we see here the nuclear reaction. The fluorine-18 decays into oxygen-18 plus a positron, that anti-electron that came from a proton being converted into a neutron. So that's why our mass number stayed the same from left to right, but our proton count decreased from 9 in fluorine to 8 for oxygen, plus that positron, the positive charge portion of the proton, was emitted when that proton was converted into a neutron. So here we see a result of someone who's been, 2 patients actually who've been dosed by that fluorine-18, and the PET scans show on the left side the brain of a normal person after imaging with positron emission tomography following the dosage with radioactive fluorine-18, and then on the right hand side we see the brain PET scan of a patient affected by Alzheimer's disease, and clearly it's obvious there are certain regions of different activity going on there in the brain of the normal patient versus the Alzheimer's disease patient on the right side. Here's another imaging technique, magnetic resonance imaging, MRI, that actually involves the nucleus but is not a nuclear medicine technique. So in chemistry we use this a lot for determining different environments of hydrogen atoms in organic compounds typically, and we call it nuclear magnetic resonance. When that same application is done in medicine, they call it magnetic resonance imaging because they don't want people to be concerned about the nucleus. It's not a nuclear technique like a PET scan that involves a nuclear decay of a positron. Here, it's a very powerful technique that doesn't involve X-ray radiation, doesn't involve high energy radiation at all. It's just a straight imaging technique where it's the least invasive imaging method available. It does take some time. You have to typically try to remain motionless for half an hour or more. It's often in a very tight area, so claustrophobic patients, they try to have open MRIs, but some people who are really claustrophobic can't even handle those. So it does involve putting the patient in a fairly tight space for a fairly prolonged period of time. So although it has the benefits of being non-invasive, it does limit the type of person you can test by this method if they really do object to that sort of environment. It's based on absorption of energy when the protons, the nucleus of these hydrogen atoms, and we're very much water-based, so we have lots and lots of hydrogen atoms in all those water molecules and all the protein molecules as well. There's tons of hydrogen present in the human body. So if you expose the nuclei of these hydrogen atoms to a strong magnetic field, they'll align with the field, and then as you remove the field, they'll relax back to their normal state. So those pulses of energy that vary between aligning the hydrogen protons against an applied magnetic field and then removing that by removing the pulse and allowing the hydrogen nuclei to realign as they naturally would. That repeat pulse pattern allows for a scanner to convert those different energies absorbed from that spin flipping of the nucleus of those hydrogen atoms into an image. And you can get some really nice, very detailed images this way. And again, it's not involving nuclear decay. It's just a matter of manipulating the nuclei of those hydrogen atoms. So we see here the result of an MRI, and this is a very, very nice, it's false color. It doesn't really give you any color, but the false color is nice for imaging, and it's able to image soft tissue and able to give a really good image there, as you can see here. Whereas X-ray radiation, first of all, we know that's higher energy. It's ionizing radiation, so it's undesirable for that reason, but it also tends not to give as detailed an image as we see here from the magnetic resonance imaging. Okay, so after discussing in general medical applications, either treatment of a disorder such as cancer with radioisotopes, or the use of radioisotopes for imaging, as we saw in the case of PET scans, or even an imaging technique that doesn't involve unstable nuclei decaying, but rather just rearranging the spin moment, the magnetic moment of nuclei in the case of MRI. Let's see how well we do with a learning check on these concepts. So for this learning check on this part of Chapter 4, let's see if you can answer the following question. Which of the following radioisotopes are likely to be used in nuclear medicine? Would it be A, potassium-40 with a half-life of 1.3 times 10 to the 9th years, B, potassium-42 with a half-life of 12 hours, or C, iodine-131 with a half-life of 8 days? So go ahead, think about what we've already discussed, pause the video here if you need to, and when you start back up, we'll see how you did. Okay, and this was a bit of a trick question because I didn't offer you the choice D that would be B and C, but hopefully you eliminated choice A right off because that was way too long-lived an isotope. Anything really over the 100-day mark is probably not going to be useful, and certainly something in the 10 to the 9th years is going to be far too long-lived, and we don't want to expose patients for that amount of time. So choice B, potassium-42 with a half-life of 12 hours, and choice C, iodine-131 with a half-life of 8 days. Those would both be reasonable radioisotopes for use in nuclear medicine. They are both relatively short half-lives. Potassium's useful in studying various cell processes, muscle action potentials, things that involve potassium and sodium. For instance, iodine we've already talked about with thyroid function and imaging. So either B or C would be appropriate here. So if you got tricked by that one because you just chose one, and maybe you chose potassium-42 because it was the shortest of all, then don't worry, that's very logical, and I wouldn't trick you like this come exam time. But if you're maybe attracted by A or just not sure how to answer a question like this, then please do try those homework set questions, any end of chapter questions, and then certainly see me if it's still not making sense. But if everything's going well, then I will see you for our last installment of Chapter 4 in the next video.